Section 2-5, limits involving infinity. The objective is to find limits of functions where either x becomes infinite or the limit is infinite. All right, there are three different forms of limits that we need to consider here, and we'll go through each one of those three, and we're going to look at the formal definition of each of these limits. And this looks very similar to the formal definition that you saw back in section 2 when we talked about the formal definition of a limit there. It involved a delta, an epsilon, L, and C, and so forth. So we're going to see those same types of things show up here. It's not going to be identical. It's going to be similar. So here's that formal definition. And we'll draw a sketch of this in just a minute to illustrate what this means. But it says that the limit as x goes to c of f of x is equal to plus or minus infinity. So we'll handle both directions there. If and only if, for any e greater than 0, so instead of using epsilon there, we're using e, there exists a delta greater than 0, such that the following is true. If x is within delta units of c, but not equal to c, so again, delta is some restriction around our domain here. It's a restriction around c. Then the absolute value of f of x is greater than e. Now the reason why the absolute value shows up in here is because of the fact that I'm letting this handle both the plus or minus infinity. So that's the reason why I see absolute value of f of x is greater than e here. We could rewrite that as f of x is greater than e, or f of x is less than the opposite of e. That's just the definition of what that absolute value means there. So you could write it either way, of course. The absolute value just kind of condenses that for us. All right. So let's take a look at a sketch that illustrates what this limit is trying to, what this definition is trying to indicate about a limit. And for this sketch, it turns out we're talking about a function that has a vertical asymptote. So I'm going to sketch a line here indicating a vertical asymptote for us. And I'll just sketch some function here that does something like this. It gets closer and closer to that vertical asymptote. We'll call this our function f of x. So I know that based on the last part of this definition here, it says that the absolute value of f of x is greater than e. So e is relating to the y values, and the delta is relating to the x values. So the way that this works here is we're saying we're going to pick some large number e. Again, we're saying the limit is infinite. So e is kind of representing a bigger and bigger and bigger number that we're heading to infinity. And the question is, can you come up with a corresponding restriction around c, which I'm going to draw a vertical line going down here, as well as right here, right where my function crosses that horizontal line that I sketched in there. Can I find a restriction around c, and we call this c minus delta 1 on the left side and c plus delta 2 on the right side, so that as long as I stay within this restriction that I just marked along my x-axis between c minus delta 1 and c plus delta 2, that I'm guaranteed that my function is always going to stay above this line here. And I can see in my sketch that's going to happen. As long as I stay within that restriction around c, that my function stays above this value of e. All right, so that's our first definition there. Let's take a look at the second definition. This one has a limit as x goes to infinity. So in this case, we have the limit as x goes to either plus or minus infinity. Again, we're going to handle both of them here in this definition. Limit as x goes to plus or minus infinity of f of x equals L. Our limit is L, if and only if the following is true. For any epsilon greater than 0, there exists a d greater than 0. Notice that we're using d instead of delta here, such that if the absolute value of x is greater than d, and again, the reason why we see absolute value showing up there is because of the fact that I'm using a plus or minus in my limit here. I'm letting x go to plus or minus infinity. If the absolute value of x is greater than d, then f of x is within epsilon units of L. So again, d is some sort of constraint that we're going to put on x, and epsilon is the restriction that we're putting around our limit here. Now again, you could rewrite this, so instead of using the absolute value of d, or excuse me, absolute value of x is greater than d, we could write that as x is greater than d, or that x is less than the opposite of d. Those, of course, would mean the same thing. It's up to you which way you want to remember that or know that, but those obviously are equivalent there. All right, let's look at a sketch of a function that meets this type of limit. And for this type of limit, it's a limit that would have a horizontal asymptote. So let's say that that horizontal asymptote there is at L. And let's say we've got some function that's coming up like about so, getting closer and closer to that horizontal line that we sketched in there for L. So again, from the definition, they're saying that we're going to pick some value d, that's, or excuse me, we're going to pick some value epsilon, really, really small, that's going to be a restriction around our limit. So let me sketch in two horizontal lines that will represent the restriction around our limit L. So this would be L plus epsilon up here. This would be L minus epsilon down here. And the question is, can I come up with a corresponding x value so that as long as I stay greater than this particular x value, we'll call it d, that my function always stays between these two red lines I've sketched. So again, from where my line crosses my function, I'll just drop a vertical line down there. That's the value of d. And you can see that as long as I pick values of d that are greater, or excuse me, values of x that are greater than d, pick values of x to the right of d, I can see that my function is going to stay between the restriction that I put around my limit here. Okay, and the whole idea is that if I were to make this restriction around L even smaller and smaller and smaller, I can come up with larger and larger and larger values of d. And that illustrates that as x is getting bigger and bigger and bigger, d is getting bigger and bigger and bigger. I have to pick values of x that are bigger and bigger and bigger. I can show that my function gets closer and closer and closer to this value of L because the red lines would be getting closer and closer. All right, so there's our second definition. Last definition here. This is going to be a combination, in essence, of the two that we just looked at. It's a limit as both x and f of x go to infinity. All right, so it says the limit as x goes to plus or minus infinity of f of x is equal to plus or minus infinity. If and only if, for any e greater than 0, so again, we're using e because we're letting our limit is going to infinity, there exists a d greater than 0, and again, that's d there, not delta, because of the fact that x is getting bigger and bigger and bigger, it's going to infinity, such that the following is true. If the absolute value of x is greater than d, then the absolute value of f of x is greater than e. And again, the reason why we see those absolute values show up in there again is because here I'm letting x go to plus or minus infinity, so that's why I see I have an absolute value of x. And here I see that I'm talking about a limit that's becoming infinite, and so I'm using both plus or minus infinity there, and so the absolute value handles both of those for me. You could rewrite them just like we saw in the last two definitions. I'll leave that to you to rewrite if you want to. All right, let's take a look at a graph of a function then that meets this criteria. In fact, most functions that we work with have this property, that the further we go to the right, the further the function goes up. So in other words, there's lots of functions we could sketch. I'll sketch a function that looks something like this. Your exponential functions, your power functions, your polynomial functions, all those functions have a property that looks similar to this. All right, so this says that if we pick some value, large value, because we're going to infinity, some value e, I'm going to make it this value right here. The question is, can I pick or find some value for x so that as long as I pick larger and larger values of x, my function stays above that red line. And again, I'm going to drop a vertical line right where my function intersects that horizontal line, and we call that d. And again, I should be able to see that as long as I pick values of d that are, or excuse me, values of x that are greater than d, values of x that are to the right, then I can see that my function stays above this red line. Stays above that value of e. That's the whole idea. As x gets bigger and bigger and bigger, my function is getting bigger and bigger and bigger, and thus I have an infinite limit. All right, let's take a look at a couple of other properties here that we need to talk about. And actually, the first two examples kind of lead us to these first two properties. These are listed in your book there. These are both about asymptotes, and we just saw that in the first definition of a limit, we had a vertical asymptote, and in the second definition, we had a horizontal asymptote. So this says that if the limit as x goes to either plus or minus infinity of f of x, if it's equal to a limit L, then the line y equals L is a horizontal asymptote. In fact, this is the way that we're going to show that we have horizontal asymptotes on a function, is by looking at the limit as x goes to positive infinity, as well as the limit as x goes to negative infinity. Both of those will tell us whether or not we have horizontal asymptotes. And the second property says the limit as x goes to c of the absolute value of f of x. So if that limit is equal to infinity, now we've taken the absolute value here to force this thing to be positive. And the reason for that is because sometimes we have vertical asymptotes where one side is going to negative infinity, the other side is going to positive infinity. And so because of that, I need to force both sides to be positive here in order to talk about this. So that's why we're throwing the absolute value of f of x in there. So it becomes positive on both sides. So if both sides are heading towards infinity, in other words, then x equals c is a vertical asymptote. Okay? And that's directly from what we saw in those first two definitions of limits. All right, there are a couple of special limits that we need to consider. And these deal with limits that involve infinity. So I'm going to give you a couple of examples to help illustrate that here, really. But the first one is the limit as x goes to 0, and we're going to do x going to 0 from the right side. That's what the little plus sign means there, of 1 over x. Now if you check out the form that is in, as x goes to 0, you'd have 1 divided by a 0. And I would actually say we'd write a 0 and put a little plus sign there to indicate it's going to 0 from the positive side. So I'm taking 1 divided by a really, really, really small positive number, which would make this thing go to infinity. And the reason for that is because as I take 1, in fact for any constant, divided by a really, really, really small number, you end up with a really big number. If you take 1 divided by 0.1, you get 10. 1 divided by 0.01 is 100. 1 divided by 0.001 is 1,000, and so forth. The smaller that denominator gets, the larger that quotient becomes. So that's why it's going to infinity. All right. And the next one here, same function basically, but letting x go to infinity this time. So the limit as x goes to infinity of 1 over x. That takes on the form of 1 over infinity. Again, I'm just using basically our substitution method to substitute in the value of x that we're going to there. But the question is then, what is 1 over infinity? Well, again, we're saying that's 1 divided by a really, really, really big number. So 1 divided by 10 is 0.1. 1 divided by 100 is 0.01. 1 divided by 1,000 is 0.001, and so forth. The bigger the denominator gets, the smaller the quotient becomes. In other words, it's heading to 0. So the limit is going to 0. Okay? Now, by the way, with these here, I know that in the first limit there, you see that I've got 1 divided by 0. We're not changing our rules of anything we know about division by 0. You cannot divide by 0. But remember, with the limiting process, We're not talking about what's happening right at 0 technically with this limit. That's why we say the limit as x approaches 0. Okay? So we're saying here that this is getting really, really close to 0, but it's not actually getting there. So we're not taking and actually dividing it by 0, but I'm getting really close to 0. So the way we write that is it's 1 over 0. That means that we're actually going to infinity. All right? And one last form that you should remember we've talked about already, that indeterminate form of 0 over 0. If you get 0 over 0, that's indeterminate. You have to handle that a different way. But if it's any other constant besides 0 divided by 0, that goes back to this first special limit here, and that's where we get infinity. Okay? Let's take a look at a couple of examples. Example 1 there on page 55, and I'm going to modify this a little bit here from what they're asking. They're going to ask you to do some things with the deltas and epsilons and the d's and the e's, and we're not going to do those questions. I gave you the formal definition so you understand the process there and exactly what is meant by a limit that involves infinity. But here's what we're going to do. We're just going to find these limits here, and actually I'm going to add a few more limits to this function that we're going to find. So let's say we have f of x is equal to 1 over x minus 2 plus 3. So there's our function. Now they ask you for a couple limits. Actually, they tell you what the limits are here, so I guess that will be helpful for us that we know what the limits are. But I'm going to go through and just find a few of the limits here that we would make, or that would make this function an interesting function to look at. So let's start out with the limits as x goes to plus or minus infinity. So the limit as x goes to infinity of 1 over x minus 2 plus 3. Now again, the way that you do this is you use substitution to substitute in this value of x and see what's happening here. So this would take on the form of 1 over infinity minus 2 plus 3. Now the infinity minus 2, we're taking a huge number and we're subtracting 2 from it. So a huge number minus 2 is still a huge number. We would call that infinity. So this is taking on the form of 1 over infinity plus 3. Now 1 over infinity, we just talked about that was one of our special limits here. 1 over infinity, 1 divided by a really, really big number is going to 0. So this turns out to take on the form of 0 plus 3, which turns out to give us just 3. So 3 would be the limit of this thing as x goes to infinity. All right. Now if we check out what's happening from the other direction, the limit as x goes to negative infinity of 1 over x minus 2 plus 3. Again, substitute in the negative infinity really here, so it's 1 over a negative infinity minus 2 plus 3. And if you check out the form that the denominator's in again, infinity, negative infinity minus 2, that's a really, really big negative number. And you're subtracting 2 from it, so it gets a little bit bigger. So it's still a huge number. So this is taking on the form of 1 over negative infinity plus 3. And 1 over negative infinity, that's 1 divided by a really, really big number. And that's heading to 0. Now it's technically heading to 0 from the negative side because we've got 1 over negative infinity there. But it's still going to 0. Doesn't matter where you're going to 0 from the positive or negative side, it's still heading to 0. So this is taking on the form of 0 plus 3. Which would mean that the limit is 3. Now to help you out with some of these, I would suggest, and we're going to see this in the next example here, next part of this question, sometimes I would suggest that you indicate which side of 0 you're approaching, because in some cases it's going to make a difference here. So up here in that first problem we just did, sometimes I'd suggest that you put in a 0 from the positive side and a 0 from the negative side in the second one, just so you can remember which side of 0 you're on. 0 is the only number where you have to watch out that one side you're positive, the other side you're negative. Every other number, of course, you don't have to worry about that. 0 is the only one where you change over from being positive to negative or vice versa. but in this case it wouldn't have affected it. All right, let's take a look at the limit as x goes to 2, and we're going to break this up as the limit as x goes to 2 from the right side of 1 over x minus 2 plus 3. And again, check to see what form you're in. So as you go to 2 from the right side, you'd have 1 over 2 from the right side minus 2 plus 3. Now the reason why it's important to indicate 2 from the right side is because when I subtract 2 from this, I end up getting 0. 2 minus 2, of course, gives me 0, but I'm actually talking about approaching 2 from the right-hand side here. So those are numbers that are just slightly more than 2. If I take a number slightly more than 2 and subtract 2 from it, I do approach 0, but I'm approaching 0 from the positive side. So this is 1 over 0 from the positive side plus 3. So the denominator is heading to 0 from the positive side. So 1 divided by 0, we know again is infinity, and since we're approaching from the positive side of 0, that's a positive infinity. And when we add 3 to that, that doesn't change the problem at all. This becomes, actually I should write both of those down for you. I have 1 divided by infinity, or 1 divided by 0 is infinity, plus the 3. And just like we've seen earlier, adding 3 to infinity doesn't change the problem. This is heading to infinity. All right, let's try the other side. The limit as x goes to 2 from the left side. 1 over x minus 2 plus 3. So again, just substitution. 1 over 2 from the left side minus 2 plus 3 is what we'd end up with. Again, in the denominator, 2 minus 2, that's giving us 0, but realize we're taking a number that's slightly less than 2 here. We're coming into 2 from the left side. So if I take a number slightly less than 2 and subtract 2, I'm approaching 0, but I'm actually approaching 0 from the negative side now. If, for example, it was 1.9, 1.9 minus 2 is going to give me a negative 0.1. All right? So I'm picking numbers that are slightly less than 2 and putting them in there is really what's happening. So this turns out to give me 1 divided by 0 from the negative side. Go back and make sure you understand the difference between these two examples here, so you understand how I know it's from the positive side or negative side there. I still have the plus 3. So now if I take 1 divided by 0, again that's infinity, but because I'm approaching from the negative side, it's actually 1 divided by really, really small negative numbers. So that means I'm approaching negative infinity. Plus 3 is still there. And again, as we saw earlier, negative infinity, adding 3 to that doesn't affect it at all. We just call that negative infinity. All right. And the last one, I guess, here is what happens then as we just approach 2. The limit as x goes to 2 of 1 over x minus 2 plus 3. Now for this, we have to break it down into the previous two problems that I just did. I saw from the right-hand side that my function was approaching positive infinity, and I saw from the left-hand side that my function is approaching negative infinity. Our property says if we're approaching the same limit from both sides, then that's our limit. If that's not happening, then our limit does not exist, and that's what we have here. I'm approaching positive infinity on one side, negative infinity on the other side, so the limit as x goes to 2 does not exist in this case. All right, let's take a look at one last example here. This is example 2 in the book, and they ask you again, this is a graphical representation of a function. They're going to ask us to find actually quite a few limits here. So let's just start here with a limit as x goes to negative infinity of f of x. So as x goes to negative infinity, that's over here on the right side of the graph. I'm following, or excuse me, the left side of the graph. I'm following the graph and figuring out what value am I approaching as we go further and further to the left. And it looks like it's approaching that horizontal asymptote of 2. So this is heading to 2. Limit as x goes to infinity from the right side. Now this is a common misconception about horizontal asymptotes. We actually have a horizontal asymptote on the right side. Again, the question is what value are we approaching as we go further and further to the right here? And I can see I'm oscillating back and forth around this value of 4, and I'm getting closer and closer and closer to it as I get further and further to the right. So the limit is in fact equal to 4. And I say that's a common misconception there, that that's not a horizontal asymptote. Because most people think, well, most people want to say that you can't actually cross a horizontal asymptote. That's not part of our definition. This is actually a horizontal asymptote because of the fact that as the limit goes to infinity, we're approaching some constant value. All right, so you can actually cross your horizontal asymptote. The key is, as the function oscillates back and forth around that asymptote, it has to be getting closer and closer and closer to it. And you can see that in the function there, that if I draw these kind of these lines here, you can see that the function is getting closer and closer and closer to that value. All right, a couple of other key values they wanted us to look at. Let's start at 1, I guess. They want us to look at the limit as x goes to 1. So we'll do that down below here. Let's break this up into the left side and right side. We'll do the right side first. So the limit as x goes to 1. Again, I'm looking at my graph, and as I approach 1 from the positive side, so the positive side is actually over here on the right side, so my function is heading in this direction right here. So my function is going to negative infinity. The limit as x goes to 1 from the left side. So again, looking at my graph, I'm looking at what's happening from the left side of 1. That's this part of the graph here that I'm looking at. What is the function doing? And it looks like it's going to positive infinity. And so just as we saw there in the last example, if I take the limit as x goes to 1 of f of x, because on the left side I'm heading to infinity, but from the right side it's negative infinity, that means that this limit does not exist. Okay? And the last one, I guess, for us to consider here is what's happening at 3. So the limit as x goes to 3 from the right side. So as we're heading to 3 from the right side, again, I'm following this curve here that it's oscillating back and forth, but as I approach 3, I can see I'm approaching just one value. From the right side, it looks like I'm approaching that value of 2. And the limit as x goes to 3 from the left side, again, following my curve, I can see I'm heading in this direction right here. I'm heading up to that value of 6. And so then the question is, well, what's happening at 3? If we just say the limit as x goes to 3 of f of x, because I'm approaching one value from one side, a different value from the other side, again, the limit here does not exist. Now, we talked about this one before, that we have a step discontinuity there. So we already know that the limit does not exist at a step discontinuity. Here's why. All right, the limits from the two sides are different. All right, that is the end of this section there for us.